All right, let's do the steady state approximation part 2. So let me just pull up the question here. Again, guys, I will try and be neat because some of you let me know that I was very, very messy last video. So I'm going to try my best to keep it nice and neat. Okay, what font do we like? This font? So let's switch the color. That's no fun. K1 over K minus 1. It gives us C plus D. I'm going to switch to this middle font for this one. And then we also have C plus A. K2 gives us E. Okay, so what's the first thing we have to do with the steady state? Identify an intermediate. And before that, I should say this is a trickier version of the steady state because we're not given which step is slow and which step is fast. So if we were given, let's say, this step were the slow step, well, we can easily go into the steady state, and not easily, but we can go right into the steady state and say that the initial rate is equal to K2 times C times A because the rate of reaction is always determined by the slow step. In this case, we don't know which step is the slow step. So the slow step could be the first step, could be the second step. So in that case, what we do is we always make the assumption that V naught is equal to the step that leads to product formation. So in this case, it turns out that the step that leads to product formation is K2 times C times A. Okay? And so we assume that that's the overall rate of reaction. So now, let's do the steady state approximation. So we know that from last video that the steady state approximation assumes that the delta T, the concentration of our intermediate I is constant. And that's a fancy way of saying that the rate of formation is equal to the rate of consumption. So first thing we have to ask ourselves in the steady state is, what's the intermediate? Well, we know that C is being made in one step and being used in another. So that C is our intermediate. And so, we got a problem in that rate step because we want to get rid of that C. So let's write an expression for the rate of formation of C and the rate of consumption of C. Rate of formation is going to be K1 times A times B. Rate of consumption of C is going to be equal to K minus 1 C times D, which is the reverse step. Going back to the reactants is K minus 1 CD. And also, C is being used up in the following step, K2 times CA goes to E. All right, so let's equal these two things together. The rate of formation of C is equal to the rate of consumption of C. I don't have enough room here. Equal to the rate of consumption of C. All right, and then so what we always do in the steady state is we isolate for the C. So let's isolate for C. I'm going to skip a couple steps, but K1A times B is equal to, divided by K minus 1D plus K2A, concentration of A, of course, is equal to RC. Look at that, I got a new color for RC. All right, so now the difficult part of the steady state approximation, or the tricky part in this example, is determining which approximation to make. So we can make, on the one hand, we can make the approximation that, well, since we have two terms on the bottom, we want to get rid of one of those terms. So we can make the approximation that either k minus 1 is much, much, much greater than k2, which means that rate of reaction is much faster, or k2 is much, much greater than k minus 1. In the second case, if k2 were much greater than k minus 1, k2 plus k minus 1 would just be equal to k2, because a really big number times a really small number is just a really big number, or plus a small number, I should say. In the first case, k minus 1, if k minus 1 were much bigger than k2, we know k minus 1 plus k2 would be equal to k1. So now the tricky part is looking at which approximation do we want to make? Which assumption do we want to make? And so for that, we look at the original equation. We know that we want an a in that original equation. So is there one approximation that would eliminate the a? So let's say k2 were much greater than k minus 1. That would mean k2 plus k minus 1 would be equal to k2a. So then, based on that logic, all of the k minus 1 term would disappear, because we said that k2, if k2 were much greater than k minus 1, then k2 plus k minus 1 would be equal to k2. So then this whole thing would cancel out to be equal to, well, this k2 would cancel out. Sorry, this a would cancel out, this would cancel out. So we'd be left with k1 over k2 times the concentration of B. So now I'm looking at the original equation. If we sub that in for C, if we sub this B, this whole expression for C in for C up here, well, then there'd be funny cancellation happening with this k2 and this k2, if you can follow me. This k2 would erase this k2 on the bottom. And so in the steady state approximation, where we typically see something like k1, k2 over k minus 1 is equal to k observed, well, we just have, in that case, k1 over k minus 1 is equal to k observed, because the k2's canceled out. Or in this case, we wouldn't even have k minus 1. We would simply have that k1 b, k1 ab is equal to the initial rate of reaction. So that would mean k1 would be equal to k observed. But how can k1 be equal to k observed? Because we said k1 was equal to the rate constant for this forward reaction here. So I don't think k1 can be equal to k observed. So long story short, I'm going to say that we make the other approximation. That we say that, just erase all of that. Let's erase all of that, because we're not going to go down that route. So in that case, we're going to make the approximation that k minus 1 is much greater than k2. And so in that case, k minus 1 plus k2 would just be equal to k minus 1. Okay, so in that case, rewriting the expression, now that we have this fact, we can say that k1 times the concentration of A times the concentration of B divided by k minus 1 divided by k minus 1d is equal to the concentration of C. And plugging that back into our original equation up here for the assumed overall rate law, then we know that V naught is equal to K2. Bringing out the K's here, bringing out the K's, K2 times K1 over K minus 1. A squared B, that's a B, over D. All right, and so this is something that looks a lot more familiar in the steady state approximation when we let K2, K1 over K minus 1 be equal to K observed. And so now we know that the overall rate law is equal to K observed times a squared. And again, that a squared was from that extra a that was just chilling outside from our initial approximation, from our initial assumption, I should say. Is equal to a squared b. Again, I can't fit those b's on the page. A squared b over the concentration of d. And so if I'm looking at my question sheet, I have the 4 multiple choice options here. It turns out that overall rate law is one of the options. We know that K1, K2 over K minus 1 is K observed. And then we're left with an A squared times the concentration of B over the concentration of D. And that is our overall rate law. I hope that helped. And so just to reiterate, when we don't know which step's the slow step and which step's the fast step, then we have to make that assumption, or we have to decide which assumption to make. We have to pick whether we want to make K minus 1 much greater than K2, or whether we want to make K2 much greater than K minus 1. And so I suggest that in this case we make K minus 1 much greater than K2, because if we just made K2 much greater than K minus 1, then we have a funny cancellation going on with the K2 from the leftover part here. There'd be a funny cancellation going on with this K2 here. And instead, if we make the other approximation, then we have a nice K2, K1 over K minus 1, which is what we typically see from the steady state. So I hope this helps. Thanks so much for watching, and we'll see you next time.